During the second half of the 19th century, more than 1,000 ships sailed into these harbour waters. They were part of a fleet that brought a human cargo from England to New Zealand. Immigrants by the boatload. It was the end of a dangerous voyage halfway around the world. 4 months spent at sea. When the first settlers arrived in Auckland's harbour, these rocks were bare. Fresh perils awaited those early migrant ships on a coastline bereft of navigational aids. Bean Rock here in the centre of the approaches to the harbour claimed its first victim in 1840. Others were to follow. So, they built a lighthouse. This is a particularly colonial structure. That top section looks very much like a house with that veranda. But this is no simple dwelling, no product of just architectural design. To place this structure in the harbour to withstand the elements required the work of an engineer. And this lighthouse was built at a time when in Victorian Britain the difference between architecture and engineering was becoming very evident in the public mind. In a rain-swept South Island inlet lies another reminder of those migrant fleets. This is the hulk of the Edwin Fox, the last of the East Indiamen. As immigrants set out in ships like this, the leading British engineers of the day were becoming household names. Rennie, Telford, Brunel and Stevenson. The Industrial Revolution was at its height. It was the age of steam. Only 2 years after the birth of colonial New Zealand at Waitangi, Brunel was constructing this tunnel under the Thames. The locomotives of George Stephenson and his son Robert were transforming British society. These new railways needed bridges and tunnels, and the men to design them. These great projects, huge even by today's standards, were opened with ceremony and fanfare. Their builders became the superstars of the age. They were innovators in the use of materials and manpower, and most importantly, they passed on their new ideas to others. The engineering traditions established at this time were to spread throughout the Victorian Empire. It's interesting how those early engineers, like engineers do today, saw themselves as practicing an art, not an exact science, an art concerned with resources, with landscape, with energy, with environment, with the great sources of powers in nature. Amongst the first immigrants who came out to New Zealand in ships like this were a handful of engineers. They were true civil engineers of their day, able to turn their hand to any aspect of design and construction. They had to be in a country like this, cut off as they were from their Victorian industrial base. They were a special breed, attracted by the challenges of a new land. Those early lighthouses were like beacons, an aiming point for those new arrivals, marking the scattered pockets of settlement around our coast. Of course, some engineers came out as immigrants, but others like Edward Roberts of the Royal Engineers were brought out as early as 1847 to construct military works. This is Roberts' monument, the first lighthouse built in New Zealand. He turned from building barracks to become colonial engineer to the New Zealand government. His design for Pinkaro Head was probably a world first. Why? It's of cast iron, specifically to resist the earthquakes for which Wellington was well known, even in those colonial days. This structure was manufactured in Britain and shipped out for fabrication on this spot in 1859. Those early lighthouses were vital to the development of the young colony. Roads were almost non-existent outside the settlements. The only means of communication was by sea. It was slow and leisurely transport. Much of that shipping guided by those early lighthouses were small craft like this, flat-bottomed to get up tidal creeks, wide to carry surprisingly large cargoes. Often those cargoes were timber, for timber was the most readily available resource for both engineering structures and for building. Ships like the Echo here were being built up Northland rivers, close to the great kauri forests. The Echo's birthplace, the Waterwheel River near Dargaville in Northland, was the heartland of the early timber milling industry. Kauri was king in the boom years of the 1880s. In the middle of the last century, the upper part of the North Island was covered with tens of thousands of hectares of dense kauri forest. However much we may decry the loss of this today, to the early settlers it seemed like an inexhaustible resource. Timber for ships, for cities, for bridges. The engineer became the servant of commercial appetites, providing the machinery for its logging and milling, providing the ports for its shipping. In 1905, the year the Scow Echo was launched, there were over 400 sawmills working on forests like this. Little remains of these today, but relics and museums. But from these we can still get a good idea of the difficulties in winning this resource. This is typical of the kauri logs hauled out of the forests in those early days. To move such giants, the bushmen used improvised engineering at its best. Things weren't made to last, but they were made to work simply and effectively, using in the main local materials. Look at the simplicity of these wooden rails locked into place with wedges. Some of these bush railways would have rivaled mainline engineering for their complexity. These structures may seem crude alongside the great projects of Victorian England, but remember that here there was no industrial power base nearby. Miles from anywhere, this was do-it-yourself engineering on a grand scale. The engineering degrees these men held are from the University of the Bush. Extraordinary weights were moved by equipment as basic as this timber jack, but considerable skill was required in knowing just where to apply leverage. This simple device is still in use at one of the very few kauri sawmills surviving to the present day. Here at Totara North on the east coast of Northland, Lane's sawmill is processing some of the very last available large kauri logs. The huge vertical saw is an antique, and the man supervising the operation, Stephen Lane, is a descendant from the original owning family.
I'm the fourth generation that's been involved with this mill, and we've been in business approximately 110 years, give or take a year or two. It was my great-great-grandfather that started this mill. At that stage, this mill wasn't so much a timber mill as a shipbuilding yard, and it continued to build ships through till the turn of the century, perhaps a little later, and then it passed from dual ownership, that was in the name of Lane and Brown, into the name Lane and Sons, and converted mainly to timber production.
And other than kauri for ships, was kauri used for other building purposes?
I would imagine in that period of time, during that period of time, houses would have been built in the area with kauri timber, and of course most of the bigger buildings around here would have been made out of timber from this mill and other mills around the district. There's not a great deal of kauri coming through this mill today. Mainly it's private timber whom we cut for people. It's still being mainly used in the boat building industry. However, the rougher grades are used in panelling in houses and in furniture and wood turning and a variety of other craft uses.
Just across the harbour from Totara North is the settlement of Whangaroa, the location of what is recorded as New Zealand's first engineering work. 1 kilometre of road was constructed here in 1820 in order to drag 25-metre kauri spars out of the forest for carrying back to England on the Admiralty ship Dromedary. But kauri was used not just for ship spars nor for boat building. The young colony needed timber for housing and for public buildings. Kauri weatherboarding clads the old government buildings here in the capital city of Wellington. Built in 1875, it was constructed, like many buildings of that time, in timber to withstand earthquakes. The colonial architect, William Clayton, argued for stone construction on the basis of fire risk, but he was overruled. And we now have here the largest wooden building in the southern hemisphere. You notice that Clayton was not to be outdone by being overruled in the use of stone, and he has adapted the use of kauri to create the impression of stone in a style typical of the Britain from which the early engineers and architects came. Although the heyday of exploitation of the kauri forest is long gone, timber is not an engineering material of the past. Pinus radiata, brought in from Canada, was found ideally suited to New Zealand's climate and soils, and massive pine forest developments now provide a resource for a new age of timber. These stacks are now not just destined for traditional house building. Although Pinus radiata provides relatively short lengths to work with, modern manufacturing processes are available to convert these into surprisingly large structural systems. Pat Simpringham of Carter Holt explains.
Radiata trees are milled in the short length of 6 metres, and the mills are constructed to in fact be able to cope with lengths that long. What we do is we take the graded pieces of timber that are delivered to the factories and assess them again, remove the unwanted knots from those pieces of timber. So we're actually making the timber quite a bit shorter than 6 metres. After that, of course, we join them up into long lengths by finger jointing. The finger joints are of known strength and well tested and proved. We can thus build up a beam of considerable length, say the longest that I know of are about 44 metres, and these are in fact much bigger or much longer than the old timbers that were available there, perhaps from sawing the kauri logs we had of yesteryear. We can mould it into shapes. It doesn't have to be straight. We can curve it and to make any shape that we desire, the shape to suit the structure that we happen to be working on.
Glue-laminated structural timber systems give engineers a product which weight for weight is as strong as steel, amazingly fire resistant and earthquake resistant as well.
Timber structures are excellent in earthquakes. The natural resilience of the timber is the first value, which is of considerable importance, but then in addition to that, the natural lightness of the overall structure. We have less weight to actually carry in the earthquake, and this is the fundamental reason why, say, New Zealand houses are excellent earthquake-resistant structures. We carry this principle on into larger structures, commercial and industrial factories, 2- and 3-storied buildings. Civil engineers, structural engineers, architects are aware now of the benefits of structural timber. Their knowledge is the real essence on how to build in timber.
As we have seen in the example of this building, its architect Clayton came to New Zealand from a Britain where engineers, architects and craftsmen were more used to working in stone and brick than in timber.
The stone has a remarkable uniformity of colour and texture. Not only can large blocks be got of the same tint and consistency, but whole cities might be built in which one stone could not be distinguished from another.
That was written in 1879 by distinguished pioneer engineer William Blair. He was talking about Oamaru stone. Whereas in the North Island, timber was the premier building material, here in the South Island, engineers and architects found a whole range of rocks to use for construction purposes. This creamy, hard limestone was an excellent structural and building material. It was used in bridges and in major public and commercial buildings for both engineering and architectural purposes. South Island stone was not only in demand locally, but was exported in great quantities to Australia. From this quarry at Mount Somers, where the Canterbury Plains meet the foothills of the Southern Alps, thousands of tons of quarried limestone were shipped to Melbourne during the 1870s. Oamaru stone and Mount Somers stone were also shipped north to Auckland. Oamaru stone for the town hall, Mount Somers stone for the university. But stone structures, just like timber structures, still require maintenance. When the arts block of the university was opened in 1926, its white Mount Somers stone led to it being dubbed the wedding cake. Now the Mount Somers quarry has been reopened to provide matching stone for repairs. And when the cleaning work is complete, Auckland's wedding cake will be re-iced. But to the early settlers, stone was not just a basic ingredient in providing shelter. It had a most important use in providing food. These millstones of quartzite rock are all that remain of Auckland's most well-known flour mill. Built in 1851, Partington's mill, like a beacon, dominated the Auckland skyline for 100 years. It gained its power from the wind blowing over the Karangahape Ridge. If we look back through the colonial records for 1855, we find there were some 13 flour mills in operation in different parts of New Zealand. Another 5 under construction and 7 more were planned. Partington's was the most notable of the few wind-driven mills, but most flour mills were driven by water power. The largest water wheel in existence in New Zealand is here at the site of the old Phoenix flour mill in Oamaru. It's over 10 metres in diameter, has 84 buckets, and was built by a local foundry in iron, a new engineering material in the 1870s, but one that was beginning to have an impact on the development of the country's resources. The Kawana flour mill, here on the bank of the Wanganui River and built in 1854, is the sole survivor of many which operated on the river. Sir George Grey, governor at this time, presented the local Maori people with the millstones. The word Kawana is a Maori transliteration of governor, and hence this mill commemorates Grey's gift. Apart from the gearing, this whole structure is constructed in wood, the 5-metre diameter water wheel being probably the oldest still in existence in New Zealand. It was powered by a stream diverted to take advantage of the water drop over the steep banks of the river here. This water wheel is high in the hills above Bannockburn in central Otago. It's a lonely site, far from the nearest river. Why engineers erected this machinery and how they powered it begins our next program.